All right, good morning. Here we are yet again for another lovely session of MENG 3310 Fluid Mechanics. This is going to be the 25th lecture in the video series, and today we're continuing on with the discussion. With our discussion of pi terms, moving on to modeling them as functions or finding the functions therein, and also maybe looking a bit at similitude if we have time. Okay, so what I want to look at is, I have a few objectives here. First, I want to discuss how we correlate data to functions, and second, how we would apply, say, Excel to find functions in an experimental setting. So correlating data. Let us consider correlating data. All right, so say we have a system that we look at, say, delta P is a function of V, D, mu, and rho. So very similar to what we looked at previously. And we have learned if we have an experimental system like this with 5 variables, we could then translate this into a system of 2-dimensionless numbers. Two-dimensionless numbers. And these would be your pi terms. So for example, in the previous problem, it was d delta p over rho v squared is some function, this phi, of rho vd over mu. And so we kind of glossed over this term here, this function, this phi here. But what does this actually mean? So we want to know, how are the numbers related? How are these two numbers, if I can spell properly. How are these numbers related? In other words, we need to correlate the variables. And this will be very similar to what you've seen in previous, especially more fundamental classes like, I know at HCC we have the Programming for Engineers course, that ENGR 2304, which goes into a lot of stuff on MATLAB, on Excel, and some other programs. But you need to use a lot of the techniques from that kind of coursework. So to find phi, you first need to find the function form. The first step is to find the function form. What I mean by that is the mathematical function family. So you might have, there's different forms you might have. You might have pi 1 is m times pi 2 plus b. What mathematical equation would this be? This is what form?
Slope-intercept.
Or slope-intercept, yes, which I would just classify that as linear. So this would be linear. You could have something like pi 1 equals a times pi 2, I don't know, to the third, plus b times pi 2 squared, dot, dot, dot. I would call this polynomial. There could be a polynomial correlation. You could also have, I don't know, something like pi 1 equals a times the log. Well, a times the log of pi 2 plus b, and this would be logarithmic, or you could say something like pi 1 is a times e to the negative b times pi 2, and this would be exponential. There are many, and you could even have something sinusoidal perhaps. There are a whole bunch of potential mathematical forms for these things. And this can be very difficult. There is very difficult, extremely difficult, essentially impossible to do by hand. No, there is no one way we usually use software. usually use software. So Excel or MATLAB or some other data analysis package in order to find the form. So the first step is just to find the family, the function form. And you would do this using software, using, sometimes you might actually use your judgment. If it's a system that you feel would likely have a linear form or an exponential, if you know something about the system and know how it behaves, then that might be an instance where you might just immediately assume a form. So for example, if a classic example would be something like radioactive decay. That would be a system where I know there's going to be some sort of exponential form there rather than linear or that kind of thing. So that would be a case where I already know the system ahead of time or the form of it ahead of time. So the first step again is to find the function form, and the second will be to find the parameter values. In other words, this would be the find A and B, the constants of your function form, whatever that may be. Okay, so now this is something that I definitely wouldn't ask you to do during the exam. Except, I might ask basic principles or something like that. But if I'm asking you, I'm not going to get, when I say that you can only use a hand calculator on the exam, I'm not going to be asking you to do a logarithmic regression. Find this log function based on this set of data that using this hand calculator. That would be a bit evil. I'm evil, but I'm not quite that evil. So anyway. Yes. Anyway, so let us look at curve fitting or regression. A few notes on this. Or regression. So a few notes on this. Then, if I don't go to the next slide too early. Or regression. So again, this is best performed via software. If I need to do it, I'm almost always using Excel, but you can also use MATLAB or numerous other programs. Well, Excel would really depend on the nice thing about Excel is it's very user-friendly, but it can be limited in the amount of data that you can work with. It's a resource hog, so you got to be careful with that. Now Excel, you can simply, if you want to, you can simply add trend line. You click add trend line on the graph of a set of data on a scatter chart, and then you can select different forms that you want it to estimate, whether that's logarithmic, exponential, what have you. Now, sometimes you can have a case where the simplest case of data analysis they might have to perform for this, or the simplest case of a pi term. What if you have pi 1 is equal to phi? What does this mean? Pi 1 is equal to phi. Not phi of pi 2, not phi of pi 2 and pi 3, just phi. In this case, you might have a case where, imagine if you had 4 variables and you had 3 reference dimensions. In that case, you could reduce the system to only 1 pi term. So you would have only 1 pi term. And the phi would just be a constant. Only 1 pi value. And this would, there would be no curve fitting required. So this might be the type of thing I gave you on an exam. That'd be very easy to put on an exam. Because then you wouldn't have to do any kind of very fancy, very involved, I should say, linear or polynomial regression. And then, of course, phi is essentially just a constant, just a set mathematical value. And the other neat thing about this is only 1 data point is needed to evaluate. Only 1 data point needed to evaluate. If all of this stuff simply comes to a constant, all I need is a single known point, and I can find that function because there's only one unknown, and that is phi itself. It's a constant. All right, so let me work through an example here. So say I have a ball settling in a fluid, say a viscous fluid. Imagine I have a ball that is in a fairly viscous fluid. Ball settling in fluid. In fluid. So if we had, if you have a ball passing through, say, air or something like that, that is a very low density, very low viscosity fluid, for very common velocities, a stone or a heavy ball or something like that will pass through essentially undisturbed, except if you're going over long distances. Often cases for simple problems, you can even ignore air resistance, although when we get to lift, we'll see that's not always the case. But for a very viscous fluid, the drag forces will dominate. So we might say that the velocity, the final velocity, is maybe a function of d. Let's say I determine that it's a function of diameter d, delta g, the change in pressure, or sorry, the difference in gamma. Let me show you this, and mu. I'll define all these. V being the settling velocity. So for a very viscous fluid, it would have a very low terminal velocity. D may be the ball diameter. Delta gamma, the difference in gamma between the ball and fluid. Between ball and fluid. And mu, the mu of the fluid, the viscosity of the fluid. Now, let's say I run one experiment. And find the following. So I only do one test, and let's see what happens. Well, I just have a ball, I have a viscosity, I have a diameter, etc., etc. And let's say I have the ball diameter is 0.0083 feet. Mu is, and I'm just going to give all of these in units of feet to make things a little bit quicker, 0.03 pound-seconds per foot squared. And delta gamma is 10 pounds per cubic foot. That would mean the gamma of the ball would have to be approximately 74 pounds per cubic foot, because the gamma of water is approximately, I should say 72.4, because the gamma of water, of course, is 62.4. Anyway, and then I measure the velocity. I measure v. So I set these up as my independent variables, and then I measure that v is 0.42 feet per second. 0.42 feet per second. And what I want to do is, so all of this is given, and I want to determine how v varies with the other variables. I'm going to find or determine how the velocity varies with the other variables. So let's look at this. Well, I'm going to, just like I have done previously, I'm going to look at this from the point of view of dimensions. So I'm going to say that velocity has dimensions of Lt to the negative 1, that d has dimensions of L, delta gamma has dimensions of FL to the negative 3, and mu has dimensions of FL to the negative 2 times t. Okay? Now I'm going to select these as repeating and non-repeating. Well, I definitely want my velocity to be non-repeating, and that's because it is one of my dependent variables. So this has to be my non-repeating, because it's dependent. And here, this will be repeating, and I only need one non-repeating variable because I have 3 reference dimensions and 4 variables. That means I need 3 non-repeating variables. Or sorry, I need 3 repeating variables. So repeating, repeating, repeating. So again, I have 3 reference dimensions. That means I'll need 3 repeating variables, which will work out. And so this means that there is only going to be one pi term. So k minus r, if I do that, I find that I'll need only one pi term. K minus r equals 4 minus 3 equals 1 pi term needed. Okay, and this, and the only choice for our non-repeating is v because it's the dependent. For non-repeating is v because it's the dependent variable. The dependent variable. The dependent variable, if you prefer, if you're strange. Anyway, so questions on that so far? Okay. So let us work through this. I'm going to try to build up the pi term. I could use equations for this, but for something so simple, I'll probably just, for something as simple as this, I'll probably just do it sort of by trial and error. And so pi 1, well, it's going to have something with v. Well, velocity v, of course, has dimensions of L t to the negative 1. Then let's say I need to find a way to include all of the various terms. What happens if I multiply it by viscosity? Well, then I'll have LT times FLT, or FL to the negative 2 times T here. And this is, times the negative 1 times FL negative 2 times T. And with that, my time dimension goes away. Then I might say divide by delta gamma. So V mu over delta gamma is equal to F L to the negative 1 over FL to the negative 3. And that will come simply to L squared. However, L squared has the same units or same dimensions as D squared. So from this, I can actually make my pi term be V times mu over V times mu over delta gamma V times mu times divided by delta gamma D squared. That's going to be equal to pi 1, or which is also equal to our phi. And so then, if I plug in all of our all of the values that I got previously, if I plug in values, I find that pi 1, or that phi here, is equal to 18.1. So if you plug in all of the values I gave previously into this term, you will find that our phi is equal to 18.1. So in other words, I could then reduce this entire system to V mu over delta gamma D squared is equal to 18.1. Very useful relationship. Now I'll have a system, now I'll have a simple equation that describes the relationship between all of these variables. If I know any 3 of them, I can find the other one. All right, so here. Let us discuss perhaps 2 pi terms. So what if you have a system where there are 2 pi terms? And let's say you have one where pi 1 is equal to phi of pi 2. Okay? So say we have a system where we need 2 pi's. And this is going to get a little more complicated. So let's say we have a system where 2 pi's are needed. And in this case, we're going to need multiple data points to fit. And however, conventional fitting tools do work well. You can, if you have only 2 pi terms, you can use something like Excel very easily. If you have 3 pi terms, well, then it starts getting a little trickier. Or conventional fitting tools work well. So what you're going to do is you will essentially create a series of ordered pairs from your experimental data, and then you will plot them. You'll calculate the values of pi 2 and pi 1, or vice versa, and then you'll do a best fit line on data to find your function. You'll do some sort of best fit line on the data to find your function. All right, so let's see what I can find. All right, so let us say we look at this and we have an example where d over delta PL, or d times delta PL, say we determine through a analysis, like actually this is what we looked at previously, d delta PL, the same system as in the earlier lessons, d delta PL over rho v squared is equal some function of rho vd over mu. Rho vd over mu. And let's say I wanted to now actually find this phi. So let's say I ran some experiments. So I run some experiments using, let's say I have mu density rho equals 1,000 kilograms per cubic meter. So using some water here, mu equals 1.12 times 10 to the negative fifth Newton seconds per meter squared, and d is 0.5 meters. And then I then have a pipe that I put varying velocities through, and I get the following data. So these are going to be constant throughout the trials, but the velocity, maybe I'm going to alter the velocity and measure a change in pressure. Delta PL. Well, so maybe it's I have a series of trials, 1.1 meter per second, 2.7, and 4.4. And then maybe 30.25, 60, 87.48, and 174.24. So that is the data I got, and then we'll figure out how we could get that there. All right, so how we can get this data. And what we want to do is we want to correlate phi. And I'm not going to be able to do this directly in front of you, but we'd have to use Excel or something like that. That would take a bit more time than we have, but again, I assume you know how to do that by now. So we'd correlate phi with our experimental data. We would create a spreadsheet. If I was using Excel, I would create a spreadsheet that said meters per second, d in meters, rho kilograms per cubic meter, mu, which would be Newton seconds over meters squared, delta PL, etc. And then I'd have a column for pi 1, the calculated values of pi 1, and pi 2. So all these columns in Excel. And I would fill this whole spreadsheet out. And again, pi 1 and pi 2 would just be calculated from what we saw previously, or the formulas we've seen previously, that we actually developed. And then I just find a linear regression between pi 1 and pi 2. Or not linear, or just some sort of regression between pi 1 and pi 2. Try different forms. See which gives you the best r squared coefficient. See which gives best r squared coefficient. For example, you might find that pi 1, so if you run through this through Excel and you try a power relationship, you can find that pi 1 equals 6065.1 times x to the negative 0.741. And this will give, if you do it, you'll find that r squared here, the correlation coefficient, is equal to 0.991. So pretty good. And then so overall then, our relationship would collapse down to d delta PL over rho v squared is equal to 6065.1 times, so this is the equation I would get from Excel here. Actually, from Excel, I would get this kind of thing. Y equals this x to this. Sorry about that. But if I translate this back to pi terms, I would have rho vd over mu to the negative 0.741. So again, to find the data, or to find the equation, to find the function, the phi of our pi term sets, we first put our experimental values in columns in a spreadsheet. Then I guess you could use rows as well, but columns are usually more convenient. You calculate pi 1 and pi 2 for each of your rows, and then you run a correlation between your pi 1 and your pi 2. Although, if you wanted to get better data, we don't have that many experiments here. We only have 4. So to get better results, we would want to use a higher number of experiments to be more confident in our results. All right, so and we could also look at systems of 3 variables using some more advanced techniques. But that's the basic idea of working with finding the phi equations of pi terms. All right, so I think I might begin a discussion of similitude now. Although I might stop this here really quickly and do a second video for this.